Okay, so this is the second video in section 910, and it's going to get a little bit sticky here for a second, but don't to worry. There's just one key point that we want to take away from this video, which we'll be keen to make. So in the last video, we examined this series, right? This Maclaurin series, which was the series that we hoped converged to sine of x. What I'm going to talk about briefly in this video is I'm just going to talk about how just because you know a particular Maclaurin or Taylor series converges, that doesn't necessarily mean it only converges to the function that you're thinking it does necessarily, and where that happens can be tricky as well. So we're going to have a theorem that takes care of that sticky business. But first, let's just talk about a little bit more about what I mean. So I liked this part, this little discussion in the book. So in that example that we did in the previous video, we decided that the power series converged, but we weren't able to necessarily, I don't think, say that it converged to sine of x for all x. We just knew that it converged to some function. We didn't really know exactly what that function was. So it can easily happen that another function will like pick up these discrete values of the nth derivative when you're looking only at x equals c, and then at other x values it could be different. So if you think about this function over here and you made it into a power series, you'd get the same series that we had back here. So that might be instructive for you to do if you have some extra time, is to expand this guy into a power series. So you can see it's the sine of x between pi over 2 and pi over 2, but beyond that it's 1, and before negative pi over 2 it's negative 1. So this guy, if you do take the power series centered at 0, you get that same series that we had. So that'd be a good thing for you to try. But anyway, you know that the series converges to all x. This guy back here, let's just pretend we aren't even thinking about what function it converges to. We know it converges, but it can't converge to two separate functions, right? It can't converge to this and to sine of x for all x values. That would just be ridiculous. It cannot converge to two separate things. That's just logic. So what we're going to do is try to establish a way to decide what a particular power series, a particular Maclaurin or Taylor series does converge to, and have a tool to decide that. And I think it's a tool we've already seen. So the theorem that we saw previously said that for each n, f of x is equal to the Taylor polynomial, that's what this is, right, plus some remainder of the function x, where the remainder was this Lagrange error bound thing, right? What we want to take note is this value of z is something that we're never going to be able to directly work with. We can only bound it. What's key, though, is that if the remainder approaches 0, then we'll know what our Taylor series actually converges to. So that's kind of what we're hoping for. So here's what the theorem says. It says if the limit of that remainder term is 0 for all the x's in the interval that you're concerned with, then the Taylor series will actually converge to the function. That makes sense, right? Like if the limit of the remainder, this is a very simple statement. If the limit of this term goes to 0, then f of x, well, I should say the Taylor series, which is this part, right? The Taylor series, which is this part right here. Before we were working with it as a Taylor polynomial, but now it like keeps going and going and going, right? We've got that plus out to infinity. If this guy limits to 0, just this one term, then that series will converge to this function. So that's what this guy says. So I think it's a fairly understandable statement. So we're hoping that remainders converge to 0. That's the main thing, is we're hoping that Lagrange error bound thing goes to 0 if we take its limit. All right, so let's continue working on our previous example. Before we launch into it, though, I liked what this said. It said we derived the power series for the sine function, and we concluded that the series converged to some function on the entire real line. Okay, so the interval of convergence for this guy, I, was negative infinity to infinity. I'm not sure if we showed that. Perhaps we should have done a ratio test and showed that. Should we go back and do that right now? You know what? I think we might have time. So let's go back. up here and try to do the ratio test, shall we? So here's our function. Let's do the ratio test. So how does that go? Don't you go the limit? I haven't done it for a while here. So the limit as n approaches infinity. This might get ugly, so we're going to go n plus 1, a sub n plus 1 over a sub n. So we're going to have negative 1 times negative 1 to the n times x to the, let's see, x to the, what? If we put in n plus 1, then that's going to be 2 n times x to the, if we had 2, that would be 2, so times x to the third over 2n plus 1 factorial. If we put in n plus 1, we're going to get, what, 2 times 2n plus 3 factorial, and then we'll divide that by the other guy. So up here we're going to have 2n plus 1 factorial, and down here we're going to have what, negative 1 to the n, there we go, and x to the 2n, and x, right, x to the 2n plus 1. Okay, so let's see what that's equal to. So that's equal to, I'm going to just write lim, okay? That's equal to the limit of what? What cancels? So we've got this thing that cancels, and some of that factorial stuff cancels. The x to the 2n cancels. This guy goes down to 2 and cancels with that guy. So let's see what's left. You know what? Let's just get rid of that. Well, let's write it for now, I guess. Let's leave the negative 1 in there. All this stuff is going to cancel, right? And we're going to have, what, 2, for this part, we're going to have left 2n plus 2 and 2n plus 3. I wrote them backwards, but there you go. We have our x squared up there, right? Okay, so if we take the absolute value, then we get the limit as n, not x, approaches infinity, right? The ratio test. So we're going to have 1 over some n stuff, 1 over this stuff right here. And then that x squared does not have an n in it, so we can factor it out in front of the limit. So the limit of that stuff, that's going to be 1 over infinity, so that's going to be 0. So this is x squared times 0, which is always less than 1. So there we go. That's what we were hoping, right? So that Maclaurin series that we formed back in example 1 by the ratio test, so we could say by the ratio test, my computer's heating up again, gosh darn it. By the ratio test, the series that we have up here, whoa, yeah, you get my point though. The series converges for all x values, right? Since that limit was 0. So the interval of convergence is everything on this. We don't even have to check any endpoints because there are none. It converges for everything. So okay, let's go back to my main point here. So we basically showed that our series converged to something. We don't know what it converged to though, right? Most of our series tests before we got into power series and stuff, they didn't say what it converged to. Geometric series did, and we might have had 1 or 2 more, like we could expand it out by doing telescoping or something. But otherwise, we didn't know exactly what it converged to. So we're going to see that it actually converges to the sine of x in this example. Okay, so I think that what they say about the key observation is that although the value of z is not known, we can create an upper bound for it. Okay, that's the key. So we did that in the previous example too. I think we created, or excuse me, in the previous lesson, I think we created some upper bounds. So we're going to do that again. So we're supposed to show that what we had up here, this thing converges to sine of x actually for all x's, and that's really going to be a powerful result. So I mean, I know we've been building up to this for a while, but this is like the penultimate part of Calc 2 almost. Okay, so using the result in example 1, we want to show that this series that we created, which is this, right, if it keeps going to infinity, that's what a series means, right? We're trying to show that that thing is equal to sine of x for all x. Okay, so first we want to examine the error bound, right? So the error bound term, this this guy right here. So we need f sub n plus 1 of z. Okay, so let's go back, and f sub n plus 1 of anything is going to be plus or minus sine of x, right? So if f of x is at sine of x, it could be a sine of x, a negative sine of x, or it could be a cosine of x or negative cosine of x. There's 4 options. What's key about all those options is that they're all wave functions, which either go like this if they're sines, or like this if they're cosines, and they all are bounded by 1. Does that make sense? So the absolute value is less than 1 for every real number that we could possibly plug in if we're thinking z, so for every real number z. Therefore, for any x, we can apply Taylor's theorem back from the previous lesson and say that that remainder term, the Lagrange error bound from that theorem, which is this guy, is less than this part, we've decided, has to be less than 1 because of this particular thing about the sign being bounded by 1. So you could put a 1 right there if you wanted to. Okay. So then this guy, all we've got to say is, okay, we just saw a theorem that said if the limit of that thing is 0, then the Taylor series converges and equals f of x. So that's a pretty nice thing. So let's take the limit of this guy. So the limit as n approaches infinity of that remainder term, which we've just established is this, what's that going to be? So it's going to be the limit of x to the n plus 1 over n plus 1 factorial. So if you think about this, just with limit laws, the only way we're going to be able to, well, I don't know, I guess we might be able to do it another way, but the way I'm going to do it is that's an exponential, that's a factorial. We've talked many times how factorial is the fastest kind of growth. Excuse me. So that limit is going to be equal to 1 over infinity eventually, which is going to be 0. So indeed, we have shown that this series has a remainder term that limits to 0. That's key. That's what we're looking for. Hence, we can conclude that this Maclaurin series does converge to sine of x, and it does so not just for some little interval. Remember, we just went up and showed that it converges on that entire number line. So that's what's really key, is that we've basically just shown or proven, maybe not quite proven, but pretty close to a proof of showing that if we take the Maclaurin series for that we had up there for this guy right here, and we make it go all the way out, then it's going to converge to sine of x. So here's a nice visual of that. So here's the third Maclaurin approximator. Here's the 5th order Maclaurin approximator. Here's the 7th order Maclaurin approximator. Look at what's happening. So the approximator's in gray. So it fits it kind of around the neighborhood of 0 pretty well for the 3rd order. Then for the 5th order, you can see how it moved out a little further. And then for the 7th order, you can see how it's continuing to fit it better and better, and it's moving out a little farther each time. So if you actually take this guy and you have that guy approach infinity and do the entire series, then the series that we're talking about here does converge to sine of x, and it'll eventually just wrap itself all the way around that sine of x to positive infinity and back to negative infinity. Okay, hope you found this useful. We'll try to do some more practical examples in the next video.